welcome back. We're going to continue our examples for section 1.5 here. So here we have problem number 5. It says, find an equation for the plane containing these 3 points. All right, so now we get a little practice with that table that was in the overview video. So what do we need to do? We need to create some vectors to start with. So let's create our starting vector first. That's the easiest way usually, or the easiest part. We'll make our R0, let's just choose P for that. So that'll be 1, 3, 2. All right. Next, we need our 2 direction vectors, U and V. So let's pair Q with P to get U. This will be Q minus P. And we'll get 3 minus 1 is 2. And then -1 minus 3 is -4. And 6 minus 2 is also +4. All right, so there's our vector U. And we need another vector V. Let's use R for that one. R minus P. We don't have to use P. We could have also used Q. So 5 minus 1 is 4. 2 minus 3 is -1. And 0 minus 2 is -2. So that will give us, okay. So that'll give us our 2 vectors that we need to find the normal vector now. And remember, the normal is the cross product of the 2, U cross V. So we have 2 minus 4, 4, and 4 minus 1 minus 2. They're already written in sort of a nice way. So I'm just going to put my I, J, and K directly above them and compute the coordinates of the cross product directly from there. So we've got -4 times -2 is 8 minus -4. So that's 8 plus 4 is 12. And then J, we have 4 times 4 is 16 minus -4 is 20. And for K, last but not least, 2 times -1 is -2 minus -16. And that gives me +14, I believe. -2, +16, yes. All right, so there is my normal vector. We don't have to take this normal vector. I don't like it because the coordinates are kind of large. So let me actually make this a little bit easier. We'll take our normal vector and we'll divide everything by 2. Or, yeah, divide everything by 2. So n divided by 2 equals, that'll give me 6, 10, and 7. And now I'm going to turn this into a unit vector. So you can leave it at any one of these points so far. Like this would be fine. But these vectors have pretty large numbers, and so things like the norm might be hard to compute. So let's find the norm of n over 2. And this is going to be the square root of 36 plus 100 plus 49. Okay, and that gives me 185, I believe. So square root of 185. And I don't believe that has any nice factorizations. Let's see. We get 11535. Oh, we do have a factor of 5 in there, 25. So we can simplify this a little bit. We have 5 times 30 and 7 is 200. Wait, that doesn't make any sense. Forget it. Let's leave it like that. I'm not certain I'm not going to make a mistake. And now we can make our unit vector n hat 6, 10, 7, divide by the square root of 185. I know it looks a little bit worse actually, but this can be nicer for computing later on. So for now, we'll just write down the equation of a plane. This is, again, n dot r minus r0, and that should be equal to 0. So our vector here will be 6, 10, 7, divide by square root 185. And then we want to dot that with x minus, what was our r0? Remember, it was this vector p. X minus 1, y minus 3, and z minus 2. Set that equal to 0, and we're done. All right, so that is problem number 5. Get an equation for the plane using 3 points. All right. 6. So find the point P where the given line and plane intersect. I have to give you the line and the plane. Okay. Forgot to write these ones down, so let's do that real quick. The line is given by x equal 2 plus 3t, y equal minus 4t, and z equal 5 plus t. Our plane is going to be given by this equation, 4x plus 5y minus 2z equals 18. And I want to find the point where these guys intersect. Well, what do? If the line and the plane intersect, there should be a value of t so that these x, y, and z coordinates can be plugged into this equation and make it true. So all I need to do is plug in x, y, and z, and then solve for t, because I'll get a resulting linear equation t, and that will be easily solvable. All right, so we have 4 times 2 plus 3t plus 5 times minus 4t minus 2 times 5 plus t. And this equals 18. Now all I do is solve for t. So I've got 8 plus 12. Let's do this way. So I'll collect like terms actually. 8 plus negative 10. 8 minus 10. And then minus 18. And then we have plus 12, 4 and 3. 5 and minus 4 is negative 20. And then negative 2 and 1 is negative 2. T, this equals 0. So we get minus 20 plus, that's also going to be negative, minus 22 minus 12 is negative 10, and t equals 0. All right, so that tells me that t equals negative 2. So if t equals negative 2, I get the x, y, and z coordinates of my point P, which means that P is equal to the point given by 2 plus 3 times 2, minus 4 times 2, and 5 plus 2. Or P equals 8 minus 8, 7. That is the point of intersection of this line and this plane. All right, we're almost there. We've got 3 more problems. Find the angle between these 2 planes. Then find symmetric equations for the line of intersection. All right, so this one's a little bit tricky to think about, but we can draw a quick picture. that hopefully will illustrate what's going on. So here is one plane. And I'll put in a second plane. And we'll be able to say what the deal is here. And all right, good enough, I think. So the line of intersection is going to be that one. So there's L and L, and we'll call this pi 1, pi 2. All right. So what's going on? Well, if I draw normal vectors, call this n1 and n2, if I pull those vectors out and I draw them over here, then I've got n1 pointing in this direction, n2 pointing in this direction, and they have some angle between them. n1, n2. All right. What do we do then? Well, we find the normal vectors of these planes first. And if you remember how you get the scalar equations like this, or the linear equations, it's through a dot product, and that dot product distributes its direction numbers to x, y, and z respectively. So we can just write down n1 and 2 directly from the equations. So n1 should be 1, 1, 1. And n2 should be 1, -2, 3. Those are our two vectors now. All right, so what do? Well, we have a formula for the cosine of the angle between these vectors, and that is the dot product n1 with n2 divided by their norms. All right. So let's see, dot product of these guys gives me 1 minus 2 plus 3, and that is positive 2, I believe, on top. And then norms, 1, 1, 1 gives me a norm of root 3. And 1, 2, 3 gives me a norm of 1 plus 4 plus 9 is 14, root 14. So altogether we have 2 over the square root of 48, I think. No, 42. All right. And if we want our angle now, we can take the inverse cosine. You're welcome to use your calculator for that. And you get something along the lines of 72 degrees, hopefully. All right. So there is the angle between the two planes. Now we can attack the second part of this question. Find symmetric equations for the line of intersection. Okay, well, in order to find symmetric equations, we had to start with a vector equation. Well, what can we do then? We need a point on the line, basically. So if I'm looking at this line, if I'm going to write down symmetric equations for it, or any equation at all, I need some place to start. Well, there are lots of ways to go at this. Here's one relatively simple way. we are already given two equations here, this one and this one for the plane. Points that are on the line satisfy both of these equations, okay? And if we have a point on the line, we can look at its intersection with one of the x, y, z, or z, x coordinate planes. So all we have to do is choose a variable, set it equal to 0, and then we can solve for the x and y coordinates of that point. And then we get our z coordinate, and then that, or we'll have our z coordinate, it's 0, and then we can use that as the starting point for our line. Where do we get our direction vector from? It'll be the normal vectors. So let's do this. We have x plus y, and if we set z equal to 0 right here, so z equals 0, we get x plus y equals 1. Our second equation, x minus 2y equals 1. Okay, so if I solve this for x and y, what do I get? Let's subtract the bottom equation from the top one. That'll kill the x, and we'll get 3y equals 0, which tells me y equals 0. Okay, well, if y equals 0, then I can look back here and say x equals 1. So my R0 then should be 1, 0, 0. Look at that. It's the vector I hat. All right, now we need our direction vector v. So this has to be a vector that is in the plane for each plane. And what do we know about those vectors? Well, if you're in pi 1, then you're orthogonal to n1. If you're in pi 2, you're orthogonal to n2. If you're going to be orthogonal to both, you had better be parallel to their cross product. So we need n1 cross n2. All right, what is that going to give us here? n1 and n2. Again, I'm gonna try to avoid having to write down that big determinant wherever I want, or wherever I can. And I already have n1 and n2 cleverly written, one on top of the other, like this, and I can compute their cross product that way. So we have 3 plus 2 is 5. And then we have 1 minus 3, negative 2. And last, we have negative 2 minus 1, negative 3. And that's our direction vector. All right. So now we have exactly what we need, our starting point and our direction numbers. And at this point, if you remember the symmetric equations formula, you can just jump directly into that. So we have x minus 1 divided by our direction number 5, and that should be equal to y minus 0 divided by our direction number 2, equal to z again minus 0 divided by our direction number 3. So our symmetric equations look like this: y over 2, z over, or minus z over 3. There we go. There is the set of symmetric equations for our line L. All right, 2 more problems here, and then we'll be finished. Find the distance between these two parallel planes. Okay, so now these two problems are about distances, and we need our distance formula. So let's just write that down right from the get-go. And that way we don't have to worry about it later. This can also be helpful on tests. Always write down your formulas first, especially the ugly ones. So we have a x0 plus b y0 plus c z0 y z0 plus d equals, or sorry, divide by the square root of a squared plus b squared plus c squared. Okay. Now, this was the equation for the distance between a line and a point. We have two planes here. It tells us they're parallel. So pi 1 and pi 2 are parallel. If they weren't parallel planes, then the distance would be 0 because they would have to cross somewhere. It's one of Euclid's postulates, sort of extended to 3 dimensions, but non-parallel objects in Euclidean space do not have any distance between them. They must intersect. So it's important that we have parallel planes. We'll take that for granted in this problem. Now we need to identify what's going on here. I have a bunch of parameters, A, B, C, and D, A, B, C, and I have some numbers x0, y0, z0. Okay, so what we can do is choose one of these to be the plane in D. So let's choose pi 2 to be our plane. And then the other plane is going to be there for us to sample a point from, and that will then give us a point to plug in for x0, y0, z0. All right, so how do we do this? So to find a point in this plane, we can just choose some values for the variables. Not all of them, obviously. If you choose all of them, there's a high chance you're going to screw up and get something that doesn't work. But think of this as being like maybe z as a function of x and y. So we can pick x and y and we'll get out a z value. Because you could solve this equation for z and then it would be a function of x and y. All right, so we need our point, let's call it P. This is going to be z1 of, and let's just say 0, 0 for simplicity. Then we get our z coordinate is -2 on the bottom and 5 or -5 over 2. So we look at this equation. If I put 0 and 0 in for x and y, those two terms go away, and I'm left with just -2z equals 5. Divide by the -2, and we get that. Okay, so that's our z coordinate, which means that our point P is 0, 0, -5 halves. All right, so there's one point on the plane pi 1. Now, this is our sample point, x0, y0, z0. So that goes in there. Next, we need our normal vector, A, B, C, and D, for the plane that we're looking at, for the plane with our normal vector. And our normal vector, again, comes from the coordinates, or the coefficients there. So n2, we'll say, n2 is 5, 1, -1. Okay. But in our formula here, we also need this d thing. And that comes from right there. Remember I said that we need to rewrite this as 5x plus y minus z minus 1 equals 0, and that gives us the correct sign for d. So now we have that d there is -1. All right, now we have everything. We go ahead and plug this stuff into our formula. What do we get? D equals absolute value of, all right, A is 5. I'll rewrite that, ABC. So 5 times 0 plus 1 times 0 I'm basically doing the dot product of n with p, or with this vector right here, and plus -1 times -5/2 plus d, which is -1. Notice I have lots of negatives here, and so it is important to have that absolute value. All right, last is take the square root of the squares of these coordinates. That's just the norm of n. And so we have 25 plus 1 plus 1 is 27. Square root of 27 is 3 root 3. So this goes away, that goes away, and we get, okay, so +5/2 minus 1 divided by square root of 27. +5/2 minus 2/2, divide by that, and we have 3/2. So 3/2 times 3 root 3, or 1/2 root 3. That is our distance between these two parallel planes. Alrighty, last problem of the day. Find the distance between the lines L1 and L2 of problem number 3. So if we go back to number 3, we have these two lines. These are the ones that were specified using parametric equations. And we had to show, okay, these guys are skewed. So this is a little bit trickier, but we can do it. So let's go ahead and write those equations down again. Copy paste them here. Okay, so paste and go. All right, so here are our lines, and we want to find the distance between these guys. So they're not intersecting and they're not parallel. It means we're not going to have an easy time just attacking this blindly. So what do we do? This is a bit weird. What you want to do is think of the lines L1 and L2 as lying on parallel planes, just like in problem 8. So let's draw a quick picture of this. I'll zoom in somewhat. Here's my line L1, and here's my line L2. A little bit. And there we go. Okay. So L1 is up here, L2 is down there, and let's say we've got a couple of points on there, here, 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 and here, maybe. And now we have our direction vectors, which I want it to be straight lines, along L1 and L2, and then the vector between those 2 points at the beginning there. So what do? Well, I can translate these vectors around. I get a nice parallelepiped here. And this guy is exactly what we're looking for. That's not quite what I wanted there. Sorry. There we go. So there's our parallelepiped. Now this guy, the top and bottom are parallel in a parallelepiped. So L1 is in that top plane and L2 is in that bottom plane. So if we can find the equation of one of these planes and a point on the other plane, then we're golden. We can just use the method we used in the previous problem. So we're going to need to find the equation of a plane, which means we need two vectors to get our cross product for our normal vector. So let's use this vector and this vector, which means that we need the direction vectors from L1 and L2. So we will just write those down next. So direction vector V1 is going to be, all right, 1, 3, minus 1. And direction vector for V2 similarly is going to be 2, 1, 4. 2, 1, 4. Now, to get our normal vector, we go ahead and cross those guys. And remember, don't do more work than you have to. So 3 times 4 plus 1, 13. All right. -2 minus 4, -6. And then last 1 minus 6 minus 5. We did already do that actually, but I figured it would be good to get some practice. So n is this as our normal vector. All right, that's the normal vector in some plane. Well, we don't actually have a plane yet because we didn't choose a starting point. Let's choose a point in L2. So to get a point in L2, we have an equation, or a set of equations, parametric. So, I don't know, let's choose S equals 0. So for a point P in L2, take S equals 0, and this gives you X equals 0, Y equals 3, Z equals -3. You can also just read that off directly from the parametric equations if you want. So here is our point P. 0, 3, -3. All right, then N, I guess maybe you can call this R0 actually, to fit with our equation format and notation. So then our plane is given by N dot arbitrary R minus R0 equals 0. Okay, so if I dot these two things together with the x parts there, the x parts in this vector, we have 13 minus 6 minus 5 dot with x minus 0, y minus 3, and z plus 3. So that'll give us 13x minus 6y, and then minus 5z. And then for our d coefficient, the constant guy, we've got plus 18 from 6 and 3, and then minus 15 from 5 and 3. So this is equal to 0. And then finally, the equation of our plane is 13x minus 6y minus 5z plus 3 equals 0. All right, so now we have a plane, and the other thing that we need is a point on the line L1. Okay. Right. Okay. So now we need a point on the line L1 here. Again, easiest way to do this is just to set t equal to 0 up here. So set t equal to 0, and we'll get a point. Call this, maybe now we'll call this one P. So P in L1, t equals 0 gives us 1 minus 2, 4. So x equal 1, y equal minus 2, z equal 4. So there's our 1 minus 2, 4. And at this point, we can plug things directly into our distance formula. Again, we'll just label things as usual, x0, y0, z0. And then this is A, B, C, and D. So we've got A times x0 is 13 times 1, right? Plus B times y0 is minus 6 times minus 2. Plus C times Z0 is minus 5 times 4. And then plus D is 3. Divide by the norm of that normal vector. And we have square root of 169 plus 36 plus 25. Some big numbers. Let's see what we got. Minus minus, that's a minus. And we have 13 plus 12 minus 20 is 5, plus 3 is 8 on top. And on bottom, we get, okay, 61, 170, and 60 gives me 230. So the square root of 230 on the bottom. Hopefully I got that one correct. Yeah, I don't think we can simplify that very much or at all. And so you would have to put this into a calculator. But this is our distance between these two lines. Okay, so that's it for our examples for section 1.